Okay, I think we can start slowly. So it's really a pleasure to welcome.
Check.
Okay. Yeah, so it is really a pleasure to welcome Professor Rainer Blatt for this evening lecture. So Professor Blatt works on ion trapping, and I mean he's at the University of Innsbruck, and this is also a center where there are a lot of people on quantum optics, trapped ions, atoms, photons. So it's really a very big place for quantum optics and quantum computing, quantum simulation. It includes experimentalists and theorists. And Professor Blatt has done a variety of experiments on quantum optics, quantum computing, information, trapped ions, different kinds of ions, calcium ions, barium ions, different kinds of traps, traps at cryogenic temperatures, traps where ions also interact with cavities. And I've read many of his papers and benefited immensely from this. One of the greatest thing also about Professor Blatt's group is that there are lots of people who have come out of his group, like there's Ferdinand Schmidt-Keller, Hans Christoph Nagel, whom many of you have heard last year also, Christian Roos, Tracy Northup, and they are in very good places across the world who are doing fantastic work. So it is really, it's almost like an empire which has come out of this place, and it's really a very nice thing that we have him for this evening talk. So he will be talking about, I mean, I'm not going to talk about any of his awards or anything. It's more, it's really very good to have him here. And he will be talking about a subset of his experiments, which is on trapped calcium ions. So over to you, Professor Blatt.
Thank you very much for this kind introduction. And I apologize for having to change the schedule on a last minute note, but there was an appointment that I absolutely need to take, and thank you very much for your flexibility. As advertised, I'm going to talk tonight about the quantum computations and quantum simulations with trapped calcium ions. And here's one of our actually older ion traps, which is a nice logo for the entire talk and for this conference. So let me just show you the menu of tonight's talk. What we're going to talk about is, first of all, that I would like to make you familiar with the notion of trapped calcium ions for quantum information processing and how we do this. Then I would like to show you what we have as a toolbox available. So I'll show you the toolbox operations in order to do all this. And then I will show you what the current Innsbruck quantum computer is like and some of its characteristics. In the main part, we are coming to computation, simulations, and also to quantum measurements. And I show you how these are made with these devices. And if there's time enough in the end, I would love to talk a little bit about scalability possibilities of the ion trap quantum computer. All of this takes place at the University of Innsbruck, here in my group, Quantum Optics and Spectroscopy, but also in conjunction with the Institute for Quantum Optics and Quantum Information of the Austrian Academy of Sciences here across the street. And there's a number of sponsors that we have, of course, among the most prominently, of course, the FWF, the Austrian Funding Agency, and the European Union, but we have also other sources of funding, as you can see here. So let me just show you a schematic picture of what this is like. You have seen on the first slide an ion trap, which is the linear ion trap, linear Paul trap. And we, of course, have ions lined up in the center. And we shine in lasers to illuminate these ions, to cool them, and also some focused laser beams in order to individually address the ions. Everything is, of course, recorded via the fluorescence light here on a CCD camera. And typically, we operate with ion strings like that. That's a real typical string. We have much larger strings, up to about 100 ions in the same trap or in similar traps. And we have shorter strings depending on the application. So we are very flexible here. And if you want to read more about that, I'll refer you to the paper right here, which shows the basic characteristics. And I'll show you another one, which is a more recent one. What are we dealing with? These are experiments, as I told you, about trapped calcium ions. Calcium has this lower system, is a two-level system right here between the S1 half state and the D5 half state. That's our quantum bit. So that's a lower lying D state with a lifetime of about 1 second. But of course, the resting state is the P1 half state. And you, of course, can now uniquely detect the system on shining in laser light at 397 nanometers. So when the system is in the ground state, it's going to be bright. And this is what we call the logical one, pointing to the south pole here of the Bloch sphere. Or if the system is shelved in the excited state right here with a lifetime of about 1 second, then of course it doesn't fluoresce when we just shine a laser light right here. So this is dark. But of course, we immediately see then how this goes. This is the way of detecting the proverbial quantum jumps by electron shelving, as you know it for a long time. For the matter of describing it, we refer to this as a sigma C measurement for obvious reasons. Now, that two-level system, of course, is residing in a harmonic trap. So in fact, when we just write down the Hamiltonian for this, you have to write very many of these two-level systems, which are just different by the trap frequency nu right here. So we have a ladder scheme as indicated right here with the quantum numbers of the harmonic oscillator n and the quantum numbers for the two-level system, which is the ground state and the excited state. And that gives us, of course, various possibilities for setting the lasers right here, the detunings. Once we detune the system here to what we call the carrier transition, it scatters only light right here. But once we tune the system to the lower sideband, as indicated here, the system scatters predominantly on the lower sideband, and then it climbs down the ladder until it finally resides in the state n equals 0. That's the ground state of the harmonic oscillator. So this is what we call sideband cooling. Once we're in that limit, then of course we are left with only 3 transitions. This is the carrier transition, just dealing with the internal degree of freedom. It's the blue sideband, which just adds 1 phonon to the system, or the red sideband, which subtracts 1 phonon from the system. Other transitions are highly suppressed because of the so-called Lamb-Dicke conditions that go into the calculation of this Hamiltonian. So the carrier is actually here to manipulate the qubit, that is the internal superpositions. And the sidebands are used to create the entanglement between spin and the motion, or the qubit and the motion. That's what we call spin motion entanglement. And I would refer you to this review of modern physics that we wrote some time ago. This quantum information processing with trapped ions appears in the following way. So we have a qubit, which is just described as a single line right here. Each line notates just 1 two-level system. And then we have an algorithm written down as a sequence of single and 2 qubit gate operations. So this would be a 2 qubit operation, this would be single qubit operation, and so forth. And this represents the quantum algorithm or the quantum circuit. These individual gate operations are usually done by just carrier operations. And one of the sidebands, for technical reasons, we usually choose the blue sideband. And then we have, of course, the Bloch vector rotations with which we describe then the quantum gate operations. The analysis is, of course, made by measurements. And in order to make a measurement of, say, a more complicated system, we need to measure the density matrix of a state or a process. And that means prior to the measurement, we rotate the system to a certain basis and project it, rotating, projecting, rotating, and projecting. That's known as tomography. And for example, then we have a build state as indicated by the state right here. And then you see the fingerprint by having, say, the density matrix. This is the real part, this is the imaginary part, ideally is 0. And this is the fingerprint of this particular build state. So there's the diagonal, which is the population, and then of course the coherence is right here. And that gives you then the corresponding density matrix and the description of this build state. There's also a spectroscopic way of measuring entanglement via parity oscillations. I probably won't have the time to talk about this today. Let me summarize the toolbox operations. What do we have? Of course, we can shine in the laser, hitting all the ions at once, say along the axis, and we can do resonant manipulations. So this is one of the single qubit operations that works in a global way. But then there's also an individual operation, the local operation, by just pointing the laser to one of these ions only. then we can do this resonantly or off-resonantly, and these are also single qubit operations. But more importantly, in order to really program the system, we have to do these entangling gate operations. This is the global Metrology entangling gate operation, which works as a two-photon transition. So for example, when you just write down the ladder operators for the harmonic oscillator and all of the respective states right here, so two ions in the ground state, two in the excited state, and the mixed ones, then you see there's 4 different pathways. When you shine in laser, say in a bichromatic fashion, you just shine in simultaneously the red sideband and the blue sideband, and they all lead to the same final state. And if you just add now the various amplitudes and square it and look for the probability for the superposing these states, then you see that in the at the right time these immediate states cancel. So the dependence on the motional states cancel. So in fact, this is a highly motion insensitive gate operation and thus the entanglement. And this is a typical time and the fidelities with which we do this. All 3 blocks combined realize already a universal gate set for arbitrary quantum computation. And that's the starting point. In the meantime, we have added more operations to that one. So we have resonant manipulations, off-resonant manipulations, but we can do this also, say, at 2 ions simultaneously. So we have parallel local operations. And we can also do the Metrology gate that I've shown you here in a global fashion, now in a local fashion, meaning that we just do this to just select the 2 ions which we want to connect with, say, 2 qubit operations. All of this can be written here, it can be read here, and then subsequent references I'll give you. Coming back to this sketch, you see now we have this global beam right here that does, say, the Metrology entangling gate operations, or then the sigma C operations. These are the transverse beams that lie here, and some of them are also done in a local fashion. For the more mathematically inclined, I'll have here a summary of the toolbox operations as unitaries. And for the subsequent part of the talks, I refer to them only as boxes, so I won't write down all the unitaries in more detail. So the single qubit operations are, for example, local stack shifts. These are just given by this U1 operation. Then you also can apply, of course, this to all of them simultaneously. That would be a collective stack shift. Or you could say this in a more general way by replacing the sigma C operator by a superposition of sigma X and sigma Y in this case. So that would be a more general collective stack shift. And then, of course, then we have here the entangling gate operation. And if you just look at the description right here, the entangling gate operation is tantamount to writing down a dipole-dipole interaction, which is here important because that's the one that we need for the entanglement. In addition to that, we have developed, and I won't go to too many details here, some hiding operations which allow us to reduce and enlarge the computational subspace. We have dephasing operations for open systems, initialization operations, and a quantum cache memory. Let me just give you a few examples. Here, for example, you see that we can reduce, say, the computational subspace. If you just take this as the ground state of the harmonic of the two-level system of our qubit, this is the state 1 that I've shown you, and that would be state 0 in the -1/2 state. Then we can actually use a pi pulse on this to tune the same level right here. And then, of course, whatever we do with the 397 laser would not affect that system. So we can reduce, or by going back, enlarge the computational subspace. You can add a controlled computation, for example, by dealing with open subsystems, by just adding, say, an interaction for only a minute amount of time. And of course, we can initialize the qubit by the appropriate optical pumping techniques. More importantly, once in a while, we need, during an algorithm, we need a memory. That memory can be done in the following way. Usually you see here, that's the ellipse enclosing, say, the qubit. That's state 0 in the -1/2 state up here, and the logical 1 in the ground state, -1/2 state here of the S1/2 ground state. Now, just applying, say, pi pulses from here to this state, and from this state up to that state, and then finally concluding this with another pi pulse up here, concludes, say, the transfer of the entire qubit to, say, 2 levels in the excited D state. That D state lives roughly about a second, so we have plenty of time. The algorithms usually take only about a millisecond or a few milliseconds, where this system can reside and is unharmed any other operation. So this is a cache memory, as we call it. Now, having all these toolbox operations available, then the quantum computation breaks down into global and local operations in the following way. We start with the superposition, then we break down according to the algorithm, the quantum process in terms of all of these local and collective and selective operations, and finally end up with a superposition right here. And then the computation is just the sequence of these quantum gates, but we have to get as an output classical information. And this, of course, is done by projecting the system. So we measure and see where we find the system. In this case, for example, it would give us the state 0, 1, 1, for example, that one. This is how we operate the quantum computer. Now, the question is, you might ask, yeah, which of the operations do we actually need now for an algorithm? And in fact, sorry, there's the airport right next here. I hope it doesn't interfere too much. In fact, you have a set of operations available, as you can see here. These are the Stark shifts, these are carrier operations, Wilmer-Sørensen, and other toolbox operations that we have. And this is an overcomplete set of operations. So the question is, how do we optimize, say, an algorithm? And this is what we call an optimizing compiler for multi-qubit coherent operations. According to the PhD student who developed it, we call this the stabilizers, the Esteban Martinez. And you can find this as a reference right here if you're interested. What we actually do is the following. We start out, say, with a set of local operations and then another layer of entangling and other local operations, another, say, set of layer with entangling and local operations. And we ask ourselves, is it possible to describe the unitary, that describes the algorithm in terms of all the sequence of these gate operations? So we just want to get a unitary operation as a sequence of the gate operations that we have in our set. So we search numerically for sequence parameters that maximize the fidelity with the target univariate, and if it's converging, it stops. Otherwise, we just add another layer. In fact, everything that I'm showing right now is using this kind of an optimization. And we never need more than 2 layers. Why? I don't know. We cannot prove that this is really, but it's always converging. We cannot prove why it's converging, but it's a nice feature to use this. Of course, this is not generalizable. You could generalize this, then of course you would have solved the entire problem of quantum computation because you could do this on a classical computer. But it is usually used for subroutines, and that's the way we optimize every algorithm that we are running. To give you an idea, when we just want to implement the ToF gate, that is a controlled NOT operation, that usually requires 6 C0 gate operations plus a number of local operations. With the stabilizer, we just run it through. So this would be just the schematic scheme for that. You see, there's only 3 entangling operations, so we save quite expensive entangling operations here. If even had further constraints, we would save even more, and then we could simplify the result. And for some more complicated gate operations, like a 4-controlled NOT operation, we can just break it down in an algorithm. You see, I'm just resorting now to the graphical representation of the underlying unitaries, because otherwise it's getting too complicated. We would not have easily found that sequence, which consists of only 9 pulses, but this seems to work quite nicely. A bit more complicated is the realization of a Fredkin gate, which is a controlled swap operation. This breaks down into 18 different pulses, and you see the sequence right here. And if you want to know more, this is a paper here, but that I can refer you to, where all of these things are outlined. So let me just give you then the bit information on the Workhorse at the University of Innsbruck. Over the more recent years, we have miniaturized the entire setup, which of course was located on an optical table and the usual experimental setup. We just put everything in 2 19-inch racks, as you can see here. This is so-called action collaboration, which is one of the flagship in the themes in the flagship initiative of the European Union. And here, just to give you some results, this is a typical chain that we just get every day here. I'll show you more details of this a little later. But again, we use all of the operations right here. We use local Wilmer-Sørensen and entangling gate operations. And more important is the capabilities. The T1 time is approximately 1 second on the optical transition, and the T2 time approximates almost half a second, so we are very close to the theoretical limit. We routinely work with 20 and more ions. You see here a string of 20 ions. We already have demonstrated the 24 qubit GHZ state, and we can support all kind of languages. In fact, with the company that I'll show you later, this system and other systems are already accessible via cloud. This has also an automated tune-up. We have single qubit control, single setting Sorensen setup, and automatic setup up to 20 qubits with full connectivity. And this entire tune-up automatically is done in less than 30 seconds. So this is also listed here. This is the more recent paper on the experimental capabilities that we have. Just to give you an idea about the state of the art, you can already address in such a system 50 qubits. This is a 50 qubit ion string, and you see these individual addressing works nearly perfect. And if you really want to know more about the crosstalk, for example, here's the full entire crosstalk matrix of the 50 ion crystal. Now, of course, you're not supposed to read all these numbers. I know they are very small. I can barely read them on my big screen here. But the message is the following. If you just look at the neighboring ones where you expect the crosstalk to be biggest, the maximum crosstalk, that happens to be this element right here, is about 3.5%. On average, the nearest neighbor crosstalk is only about 1.2%, and on average, the crosstalk is less than 0.2%. So this is very precise focusing, and these things work nicely as advertised. If you just zoom in for this, and here we just do this in a resonant fashion, you see this is a maximum of 0.98 in this little matrix that we have here. This would be out of 10 ions and a minimum of 0.1%. And now, since we are mostly using off-resonant gate operations, you see this doesn't really matter. In fact, if you see the off-resonant error rate, which can be 10 to minus 8, and on average is maybe a bit bigger. So we assume that we have a negligible error just from single qubit operations in the off-resonant fashion. And this is how we operate the system. For future fault-tolerant operation, this is very important. What about the 2-qubit gate performance? That is, of course, can be benchmarked. There are other ways of doing it. The easiest way of measuring this for us is just to repeatedly apply some 2-qubit operations. So this is in a crystal as indicated here from 12 qubits. We just applied a number of 2-qubit gates. We have the same setting here for any subset of 2 qubits here for this 12-qubit register, and we take the average. We could take, for instance, this one with that one, or this one with this one, and vice versa. I'll show you a matrix in a minute. And you see the fidelity is typically 99% with automated tune-up routines, and we can get even better to a certain extent if we really optimize the system specifically. So we have good gates without crosstalk right here. Just to give you the crosstalk data for the gate operations, they're listed here. So there are 2 different ones. We are just talking about the crosstalk here with 2 qubit gates out of a 10-qubit register as indicated right here, for example. Then there's 2 errors that we are worried about. This is the phase shift on neighboring ions. That's the single qubit phase shift on spectator ions. There's a maximum of about 2.7 degrees and a minimum, and the average right here. And the dephasing, which is listed here on the spectator ions, which is typically 10 to minus 4. And if you just look at these things, so if you are just looking at the thresholds for fault-tolerant operations with our encoding, I'll come back to that a little later, it's on the order of about 10 to minus 4 to 10 to minus 5. Then you see that we are close to that. We are still working on optimizing these things every day, and we hope to reach that threshold very soon so that we really you can use our highly connected quantum register for a full fault-tolerant operation. Okay, so much for this. Just a little bit on the hardware side. As you've seen, the 2 racks are listed here, and they contain everything in this system, including the 729 nanometer generation for the qubit and the entire trap module, which is located here. I'll show you a photo and a picture a little later. This was achieved over the last 3 years by Christian Marciniak and Ivan Pokorelov, and you see the details right here. So everything is in these 2 19-inch racks, and together they consume less than 2 kilowatts of power, and they are really operating every day in our lab and replacing 2 optical tables. These are the pictures, as you see here. This is the left side, this is the right-hand side, and the entire trap module, that what usually goes is on an optical table is here, including magnetic shield, vacuum can, and everything is included right here. Okay, just a few pictures on the technical side. This is the inside the magnetic shield. This is the mechanical view and the optical view. Everything, addressing optics, everything is right here, optimized for this. And this is a drawer that can go out of the system. And otherwise, if it's in there, it's completely shielded by a magnetic shield. So now we are ready to do some physics. What we are doing these days mostly is, aside from simple computations, is mostly quantum simulation. And there are three main approaches that we are pursuing. Suppose you had a problem to compute, say a spin problem, whatever, that you describe with the Hamiltonian. And if it's really getting too hard to use on a classical computer, you just try to implement this on what we call a quantum simulator. That could be trapped atoms, or neutral atoms, could be superconducting qubits, or it could be ions. Which way do you actually do this? Now, if you have a full-blown quantum computer, then you can resort to what we call digital universal quantum simulation. That is to say, you break down the Hamiltonian into a sequence of individual gate operations. That's what I've shown you before. That would be a computation. And then you start from an initial state and you compute how the state at a certain time t behaves when you apply these unitaries in sequence. So in other words, you can simulate any model Hamiltonian, but it requires many gate operations as a sequence of these unitaries. And I'll show you how this is done in a minute. But there's a somewhat easier operation, which is also very flexible. You could just do this in analog fashion. So you start again, say, from an initial state, but then you want to implement just this unitary from this Hamiltonian. But here it requires, if you had, say, a match between the engineerable interactions and the model in the system, you could apply this in the analog fashion for a certain amount t, a certain time t, and then simply stop the system and look what happens here. The drawback is, of course, that you just run this for a certain time t, and then you have to see what you get. Whereas here you have individual gate operations, and if you had error correction available, you could correct for each individual step, which you cannot do here. This is why we resort to this as analog quantum simulation, and this is a digital one. And more recently, we have come up also with a so-called hybrid or a variational variant. This works in the following way. Suppose you had a classical computer in which you have your Hamiltonian sitting there as a computer program. So you can, for example, calculate expectation values. But the difficulty is, of course, if you really want to calculate dynamics or want to say crunch states, it's often too difficult to really do this. So you want to go to a quantum computer. The classical computer then sets a certain parameter set right here and taps into the Hilbert space, the analog quantum computer. But of course, we are not doing the entire calculation in this quantum register right here. What we do instead, we just take the address, so our problem right here in the Hilbert space, and we just measure an expectation value. And the only value we return to the classical computer is that expectation value. Then we just let the system iterate until it finally gets a result. I'll show you now examples for all of these three different procedures. Let me start with the analog quantum simulation with spin chains. Here, for technical reasons, we're using transversal excitations, and we are not using the longitudinal excitations, but otherwise, technically, it's exactly the same thing. So we have an ion string as indicated right here, and then we are applying now the bichromatic beam as you saw from the side. So we are exciting actually the motion in this direction. So in other words, you have a dipole-dipole coupling here due to that Mellmann-Sørensen cable, and this is precisely described here by this Mellmann-Sørensen operator. If we just apply a certain detuning, then we have, as you saw before, also an interaction that is described by sigma C operation. Now, this coupling matrix right here has an approximate power law that was shown many years ago with a so-called unimal exponent. Since we are exciting here in virtually at least in the motional degree of freedoms, we could have an infinite range because the motion talks to everything at once. If we just design then the parameters, that's the tunings and say the parameters of the JHs right here in a slightly different way, we get pull-up interaction, alpha would be 1. You can go up to dipole-dipole directly as you see here in this direction. In any case, what we are interested here, to make it simple, there's many other ideas, and the group of Chris Monroe and others have done differently. We just constrain our cases to the case that B is bigger than the maximum of the JIJs. So this is the biggest parameter in the system. If you rewrite it in such a case, the Hamiltonian, then you find there's a XY interaction, also so-called hopping hardcore boson model. This is what we have underlying. Again, you see the picture, the interaction. So we have this global beam now coming from the side, but we still keep the local beam to do the addressing. Otherwise, the system is essentially the same. What kind of experiments can we do? Let's start out with a string as indicated right here. Then we can, for example, invert one string right here. So we just create what's called a magnetization or a magneton in the system. Then we apply for a certain amount of time, as indicated before, the Hamiltonian by just shining in that interaction. And then, of course, due to that interaction, this magnetization spreads. That flipping a single spin right here is called, in the lingo of spin physics, a local quench. We simulate the interaction, let the system spread, and then we measure the quasi-particle dynamics, that is, where does the system end? Now, the JIJs can be adjusted if you want to know the more details according to the trap parameters, and if you want to rewrite it in terms of trap parameters, that's the way to do it. This was figured out by Kiva and Kim some time ago. Let me just give you an example of what we measure, for example. Here is in a string, in this case, it would be a 7-ion string, the ion number, and here's the time. So we just have time slices. We just let the system go, we prepare it, apply it for a certain Hamiltonian for a certain time, and then measure. So initially, of course, we find the excitation right here, but then due to the interaction, the system spreads out in a coherent fashion. And of course, there's open-ended, so there are some reflections right here. So you see it's a coherent dynamics. Initially, of course, there is no entanglement. So if you really want to calculate then the entropy and see what the entanglement really looks like, then you see you generate entanglement due to the correlations with the other spins right here. And now we have, of course, the unique possibility to address individual ions. We just could go at this time to that ion and that ion. And if you do that, then we can just find out how much are they correlated or how much are they entangled. And the measure for the entanglement is so-called is a concurrence that we can calculate. And if you now note that the concurrence is a function of time, so we just look this for spin 3 and 5, spin 2 and 6, or spin 1 and 7, and so forth, then you see and draw this as a function of time. This is really, entanglement is moving through the system in a dynamical fashion like spin waves. So we propagate entanglement, we propagate the correlations in the system. That has been studied in an analog fashion in this paper. And I don't have the time to go through all of these things. I just can give you a reference to these things. We have studied some dynamical phase transitions right here in this paper with these people right here, theoretically led by Markus Seil, or spectroscopy of these quasi-particle states just to see how they behave. In the more details, some excitations in this paper led by Christian Roos, or more recently, environment in the system transport things, which were theoretically led by Philipp Hauke and the PhD thesis of Christine Meyer. Sorry that I don't have the time to go through the details. I refer you to these papers. Let me rather switch gears and show you how we do universal quantum simulations with trapped ions. And this is work that's led in the laboratory by Christian, Ben, and Thomas on various experiments. So we just use again the string of ions, use local operations, and use, of course, the global operations as indicated before. How do we do that? Now it's time to think about a digital simulation in terms of a quantum computation. For this, we break down a Hamiltonian, the sum of parts right here that we need to individually implement. So we built each local evolution operator separately. So we form a unitary according to the local operation right here. Think of it as sigma z, as sigma x, or sigma y, or a combination. Then we can readily construct this unitary according to the rules that I've given you for the toolbox operation. Now, then there's a so-called Throttle-Sequence approximation. The entire unitary of the entire system right here can be described in the following way. Usually you would just raise this here exponentially, but very often this is not, the parts do not commute with each other, and then you're left with a Hausdorff-Baker-Campbell formula, which you really often can't really work out. But then you can approximate it by the so-called Trotter approximation or ProtoSuzuki approximation the following way. You just apply, say, the first unitary for a time slice, the second for a time slice, the third one, and so forth. Then repeat the entire sequence n times. And then it was shown a long time ago that this is a good approximation for the unitary that you can write down. So in graphical terms, if you just really want to see the gate operations, you have here one gate, another gate, and another gate, and we apply them in sequence and call this one product digital time step. And then we apply this n times until we are ready. And then finally, we have calculated in such terms by a sequence of gate operations what the dynamical behavior of the state really is as a function of time. That this is efficient for local quantum system was shown by this gentleman, Seth Lloyd, in the seminal paper already in 1996. And this is what we set out to implement already some time. I won't go through the initial steps. I just want to give you an example, which is more recent. They've really tried to apply this quantum simulation to calculating a lattice gate theory. And this is work which was experimentally done in the PhD thesis of the Esteban Martinez that you have already encountered, and of course theoretically led by Christina Muschig at that time in the group of Peter Zoller, and now professor at the University of Waterloo in Canada. What do we do with this? Now the idea is the following. We just want to simulate, for simplicity, in order to see how the system really works, the quantum electrodynamics theory in one dimension on a lattice. Our particles, fermions, are encoded in spins. These are our two-level systems of the ions. And we take it, you start simply by taking a small, say, string of, say, only 4 ions here. Of course, in order for the lattice gate theory to really hold, we need to have the we need to have the gauge fields included. They are transformed to long-range interactions, as you'll see in a minute, and I won't have the time to go through the theory work, which you find here in this paper by Christina Muschig from 2017. And then, of course, we have to implement these interactions in a stroboscopical way with laser pulses. This is what I've just shown you as a digital interaction. So what are we choosing as a model? This is the so-called Schwinger model. The Schwinger model describes pair creation out of the vacuum. When you just shine in enough interaction energy to a point, then you create out of the vacuum, say, 2 particles, a pair of particle-antiparticle right here. And if this could go on, if you had more energy right here and time. And we just want to just calculate the first step as indicated. What do we do for this? Let me just see. Here is the Hamiltonian that we implement. That Hamiltonian is already rewritten when the gauge fields are encoded in the interactions, such that we can write it down in terms of the Pauli operations. You see here a typical double-dipole interaction, now a sigma c, that just changes the basis. But we have here the particle-antiparticle creation and annihilation. This is again an operator that you've seen before, just with the neighbors right here. And this is the effective Hamiltonian for the masses, or effective particle masses, where you have to add the term which comes from the gauge field absorption in the interaction. This was done, as I said before, by hand by Christina Muschig to rewrite things in terms of the Pauli operations. So that's the Hamiltonian that we set out to implement. Now you see, actually, these are 3 different parts, and they are not commuting with each other. At least not this with that one. And so it's not easy. So we have a fermion light coupling constant right here, and the details don't matter. So you just replace the parameters of your Hamiltonian with just what you can implement in your system, which is spin-spin interaction. It's just Near-Neighbor interaction. This is just the diagonal term, the mass term, the particle masses. And what it turned out when you really rewrite that, in order to implement this, you had to program the so-called Zij points right here. Remember the Jij matrices that I've shown you before, and here they are slightly different, but they're also coefficients that determine the interaction between the respective spins in the system. Unfortunately, these are highly asymmetric, and this had to be programmed. But of course, in a system like ours, which is fully programmable, you can do that. Let me just show you how we implemented these different proto time slices. Remember, we have three different Hamiltonians here coded in color, brown, red, and yellow. So this would be the sigma c term, this would be the flip term, and this would be the mass term. And then, of course, you repeat these sequences over and over again until your time ends where you want to simulate things. This can be broken down, of course, in each individual gate operation. I'll show you here only the ZZ term because that was the complicated one, which required the entangling operations. And we can do this in the asymmetric fashion by applying the Metrology gate operations in an asymmetric fashion to the individual ions. When we do that, we of course have to start with an input state. So we have to prepare a vacuum state. That's our definition of the input state, the vacuum state for the Schwinger model. Then we have to define a throttle sequence. That throttle sequence that I've shown you here, the three different parts are right here. And we have just rearranged the order. That doesn't really matter. But this plus minus term is a tough one. Then we have the C term, and then we have the CZ term, which is also a tough one. And you see, this has to be repeated now 4 times, or even more times if you want to know more details. And eventually we have to measure the outcome of that. So we have to find the basis on which we get the right information. The total sequence in this case was about 220 gate operations before we could actually measure. To make a long story short, the pair creation was just encoded in such a way that everything in the ground state here was in a staggered state. So this is our definition. This has some technical reasons. It gives us a decoherence-free subspace. And then we wanted to create from this pair creation, where the pair is defined by just flipping these 2 internal spins. That's the pair creation. And if you now look at the particle number with this density, the particle number density versus time, then you see that out of the vacuum state that we have here, that we create after a while, then almost with perfect excitation probability, a pair here near 0.5, because with 2 particles, that's 0.5 at that point. And then this is the indication that we have created a pair of a particle-antiparticle system. And then we just want to check, of course, how well does this describe the system? This system is simple enough that you can calculate the ideal evolution, which is shown in green, as you see here. Then you can actually see what error do we expect from discretization. And they are listed in red, and the red triangles right here. You see, this is closer to what we actually expect. The experimental data are still somewhat off, as you can see here. And this can be explained by an experimental error model. So we have some depolarizing noise. The gates are not perfect, and we have to apply, after all, 220 gates to do that. But nevertheless, we can show experimentally that indeed we have created the pair. And this is the way we simulate physics in these discretized steps. That's the Throttle-Sequence approximation. Let me go one step further and let me show you how the variation quantum simulation works. That's work that was theoretically guided by Peter Zoller and Rick van Bijnen in Peter Zoller's group, and experimental, and also Christian Kokal here in Peter Zoller's group, and it was part of the thesis of Christina Meyer. The idea is to use now, say, a classical computer with a quantum computer and let the system go in turns to find the right result. Let me show you how this is supposed to work. Again, as before, we write down the Hamiltonian as a sum of Pauli products. So for example, a Hamiltonian that we have under test that could be written down as just a product here with these correlation functions that we write here. This is residing in a classical computer. And of course, once you write it down, the classical computer can perfectly calculate any expectation value right here. Then, of course, the classical computer thinks about how do I actually represent such a state by quantum computer? So I have to find out some parameters with which I can tap into the Hilbert space. And then I just measure an expectation value right here. Now, what does that mean? Tapping into the Hilbert space requires a sequence of local and entangling operations in the quantum simulator. This is done by individual addressing. We start from a certain state. Again, we start from technically that the staggered state. That's a decoherence with subspace. You have a global operation with one parameter, Then we have local operations right here, could be the same, another global operation, and so forth. So these are all the numbers of parameters there. And in the end, we have to go to a measurement basis, measure the system. Once the system is measured, we just go to the classical computer because we feed back only the measurement result. We determine in the classical computer the expectation value from the outcome, and then compare it to what the computer expected to get when he was tapping in the quantum state. So that means we have to let the system go, reiterate, and this is what we call the variational quantum procedure. Again, we take the same Hamiltonian, slightly different notation, but you see the same terms right here, and this is a slightly longer chain, but it's again about flip-flop terms here, where we have the pair creation, and this is the underlying encoding, so we just have the positrons and the electrons right here encoded in this various spin state. This is called the so-called Kogut Susskind encoding. This was also used for classical calculations, just for reference right here. Otherwise, these things work in the same way. Now, what is the outcome of such a simulation? Now, the measurement that we get is, of course, an expectation value. That expectation value is achieved in every iteration that we get during the system. And here we just draw the expectation values as a number of the iterations, because there's always then, of course, an optimization procedure behind in the classical computer that tries to determine the energies and tries to minimize the difference between what it's supposed to have and what it's actually measured, so that we just go down. But of course, since we have very many parameters, in this case it would be 10 parameters and 8 ions for the lattice-Schwinger model Hamiltonian, there could be many local minima, which you have to avoid. And for this, the classical algorithm that we use in the computer right here, the classical computer, has a stochastic component, meaning that all of these specs that you write here, they are really results that are due to the fact that the computer tries to explore the Hilbert space on whether there is another local minimum that has not yet been found, or which is even lower than what it already has found. Meaning that we do not know precisely what is the global minimum. So we have to make sure that we do not forget these things. This requires many iterations. This is what we call the exploration and the search algorithm. Once we have, say, an idea of what the minimum should be, we get then the refinement for the search algorithm. Here, again, this system is simple enough for the Schwinger model that you can calculate that. That would be the first excited state, that would be the ground state. And this is how we actually do these traces, and then we evaluate that. So it's determining then from the measurement the ground state energy is what we find in the system. So in other words, the variation algorithm that we have here is perfectly good for determining stationary values, as for instance here having the ground state. But it has also a very nice feature. Instead of programming the Hamiltonian as indicated here and calculating the expectation values, we could also determine, say, the energies, the eigenvalues that we have from a different procedure, and measure, say, again, the expectation value here and take the difference. So, and square it. And you see, that's the variance. But what does the variance tell us? If we know we have a variance which is here very zero, or say close to zero, then we know we have found an eigenstate. So it's actually an idea to verify that we are in an eigenstate or actually close to an eigenstate. But we don't know that we have found the absolute minimum. We can at least determine that we have found a value close to an eigenstate, as close as the variance allows us. Just to give you a more refined idea, this was now done with 20 ions and 15 parameters in the system. And then you see we just calculate the energy in somewhat arbitrary values right here for the Hamiltonian and get a so-called Bayesian estimate. That estimate is, of course, it has some error bars right here, and that's where it finally stops. Now the stopping criterion is not completely clear. Usually you can stop only when the number of the terms are exhausted. But of course you could go on, perhaps you can find something lower. Here we still calculate this as the theoretical value. We are not completely down here, but within the error bars we can do this. And you can see here sometimes we are even trapped in a local minimum. So for example, right here, the system just finds say somewhat high fidelity or say a global local minimum in this area, the energy is sufficiently low, but apparently it goes lower. Then this is why we need the stochasticity in the procedure. In any case, this works nicely, and as we can simulate also the system on a classical computer still with these few numbers right here, you see that the simulated results and the calculated results on the quantum simulator well are within the 2 sigma area as indicated right here. So that's what the system can give you. And as indicated here, it allows us also to verify certain experimental results, especially when we just calculate the variance of the Stringer model. The variance, as I said before, measures the closeness to the eigenstate. And in fact, after some numbers of iterations, they require, of course, more iterations in various spaces that we were able to get down to the error closer to what the error, the experimental error really is, so that we know, okay, the variance is as small as the error bar of the experiment, and then we know we have reached the eigenstate. So it's sort of self-verifying that the system has reached an eigenstate. That said, let me just briefly summarize the variational quantum circuitry right here. The quantum system, of course, does the hard part because it provides the quantum state that you're addressing by steering it from the classical computer with certain parameters. And these parameters are just the quantum operations that you use to get the gate operations going in the system. So you can reach every nook and cranny in Hilbert space. But you don't perform any computations right here differently from the analog or from the digital simulation. You just measure, you get, say, an expectation value and let the system go around. That has the advantage that it's very flexible. You don't need to generate the Hamiltonian right here in your quantum simulator. And there are no specific quantum resources required except for the quantum, state that you have to be able to do here. It's scalable for certain interesting problems. It's not scalable for everything, but it needs many repetitions. That's its drawback, and the stopping criterion is not completely clear. For a future of this, we need, of course, faster experiments. We need to speed up the feedback loop, and of course, eventually, it needs larger numbers of ions or doing things in more parallel operations that would be 2D models. Let me conclude with a few remarks on how we can optimize things by variational quantum circuits. In this case, we can optimize metrology. This is what we call these days quantum metrology. Again, the theory to this was worked out by Peter Zoller's group, especially by Raphael Kaubrügger, and the experiments were performed on the more recent quantum machine that I've shown you in the 219 Interact by Christian Marciniak and Thomas Feldkar. What do I mean with that? We talk about precision spectroscopy. We are usually doing this for frequency standards. And for example, this works in the following way. Suppose we had our qubit transition, remember the S state and the D state, and the laser, of course, has to have the same coherence as the qubit, which is, of course, a very narrow band laser. We have used this some time ago to look into frequency standards with calcium ions, and that is here the reference to that. So you just apply a pi/2 pulse, wait a certain time, and then you have a phase evolution of another pi/2 pulse and detect. And as in a typical optical atomic clock, you get such a Ramsey pattern, and with a higher resolution right here. So the lines are only a few 10 hertz wide in the optical domain. Now, just to give you the state of the art of that clock is right here. This is what we recently measured. Our laser, the two lasers were compared down to about 10 to minus 16. And so we have this number, which is just the qubit transition in the trapped calcium ion. And we have measured that number in 2009. We were slightly off. In the meantime, this number was repeatedly measured by other groups in China, in India, and other places, and not in India, in Japan. And we have done a more recent measurement because we just wanted to contribute to the CIPM by secondary standards. And this is the PhD thesis of Milena Guevara-Berg in our laboratory. But now we can improve the system. You remember we had started with a single qubit. That's the single line right here. That would be what you do for any, say, optical clockwork. And you measure the excitation and you get the line shapes. But what if you do this now with qubits? So say you have many of them, you have a register. You can do this on all of them simultaneously. Of course, you could apply simultaneously pi/2 pulse to all of them and do the same here. But that would not gain you very much, because then, of course, you have statistical averages, and this would gain you only with the square root of the number of these things. But what if you just have an encoding pulse that you're free to program? And likewise, you have a unitary here, because this is also just nothing but a unitary, but the more complicated unitary that is allowed to freely program the system. So again, as in a variational approach, we could measure the total excitation, and then we could apply some local and entangling operations and feed it back to the system. We just could really rearrange things like here and let the system go and see on whether we can actually improve the signal to noise ratio. And how does that work? Now, the goal is that we estimate such an interferometer, which is nothing but a Ramsey interferometer phase 5 on the measurement record. So we calculate again the mean squared error and make a Bayesian estimate of the phase, not the energy at this time. And of course, we have a prior phase distribution given by the problem we know that at hand with a certain width delta phi. And then we minimize the measured imposition or the variance. That is, we seek for the optimal performance of real parameters. That is, we really want to optimize the encoding and decoding procedures. How does that work? Now, suppose we start with, say, in this case, 60 lines. If we just do now the following, and this is just no encoding pulses and no decoding pulses, we just use pi/2 pulses as indicated, that would be the classical coherent spin state, what I call a standard feature. You see, this is a Ramsey fringe where the second pulse has just 90-degree phase lag with the first, so you just have a fringe that goes to 0 at this point. So you really want to stabilize your clock at this point. If you look at the mean squared error of the phase right here, which comes from the quantum projection noise, you see quantum projection noise gives you this limit right here, and the mean squared error can be determined from the signal to noise ratio and things like that. You would get a curve like this. This is where you want to be, and you want to have, of course, say a feature which automatically stabilizes the system. And you see within these points, you can actually be everywhere because the system varies. It has to be stabilized at this point. Now, if you just apply, say, a single Wilmer-Sørensen spin state to the first part that we have, say, a first iteration on the encoding right here, then you get already what we call a squeezed spin state, meaning that in the center, the noise figure just goes rapidly down. So you have less noise as indicated. So it's a spin squeeze state, this highly correlated state, the tangled state of the 69s, and that gives you access to a better signal to noise ratio. But we can do even better. We can actually say, no, let's just go for a tailored measurement as well, because we have just prepared the system in a certain spin state, and now we tailor the measurement to really optimize this. And the optimization would be not only to the signal to noise ratio, but also to the catching range. So you just have, say, much more linear line here. It's not as steep, but it has a wider range right here. And if you just look for the mean squared error, this would be this, and it really nicely coincides with what we have from the theory part from Peter Zoller's group. But again, now we can tailor both the input and the measurement. And then, as you see here, you see this speeds everything. So we get down in a wide area to the noise floor that we expect, and we can actually get lower noise and a wider catching range in this area. This can be summarized in a figure like this, where we just have the classical area. This is what you would reach with, say, it's a classical spin coherent spin state, and then you have the optimal quantum wave, which you calculate from first principles. And then, of course, you could calculate, so what do we expect if I just increase the I number? It isn't perfectly aligned with the best results that we could get. That is due to the fact that our gate operations are not exactly perfect, but they are certainly giving you several dB of gain as compared with the just simple and classical states. This is what we call an optimized Ramsey sequence, and this is quantum metrology because we can optimize a measurement by quantum features. Let me just finally conclude with a few remarks on scalability goals and strategies. What we need in order to go for more computations or for more metrology features, we need to scale the system. Scaling means scaling up, for example. We want a larger system. We need more qubits that would require different traps, 1D or 2D traps. We will need more operations, better control, less errors. We would need more computational power, the software, and we need, of course, predictability. In order to scale this up, you need to know how your component performs, but you also need to know, does the entire system then behave as if you just add the performance from individual parts? This is not always a given. On the other hand, you need scaling to scale down. You want to miniaturize the system. Remember, we have already put everything into a 19-inch rack. This is space constraints. So control hardware needs to be smaller. It's better to be controlled. But you need also to have less errors. You need protection schemes, passive and error corrections. That would be the active way of doing this. And we need faster gate operations in order to have things on a shorter time scale. But what has usually not been considered so far is what I call scaling out, or that's the interconnectivity. In order to have, say, for example, distributed quantum computation, you need quantum parallel hardware and quantum parallel software to do this. This would be the distributivity. And this is all needs to be tackled. And we are working on this in the group, but I wouldn't have the time to go through all of this. Let me just give you one example in the last 2-3 minutes, which is what we call keeping a qubit alive. This is actually the quest for a scalable ion-trap quantum computer, which really can do long calculations. And this is work that is theoretically guided by Markus Müller and experimentally guided by Thomas Mons in our group. Let me just give you an idea. Don't worry about all the details of this slide, which is way too complicated. What we need to do is we just have to encode one qubit into a set of physical qubits for error correction. We call this a logical qubit. So in other words, this goes with a sequence of gate operations. And we call this simply color code because according to bookkeeping, we can just colorize these plaquettes, and then we can measure stabilizers that help us to figure out which error was there, and then we can correct for it. In any case, so you really want to have logical qubits because that allows you then to go for error correction. And this requires now a certain the trap architecture. So for example, suppose the 7 ions that I showed you before, they carry the logical qubit. But then you have to do error correction, so you have to figure out, did something happen here? So that whether something happens, it can be measured immediately by talking to so-called ancillars. These ancillars are helper ions that help you find out where was the error, how can we correct it. More recently, we have seen there's another protocol that allows you also to see whether there's an error that spreads to the system. So this is the error spreading in the system that you otherwise cannot control. But so it requires essentially a long string right here, where only 7 of them have a logical qubit. But then, of course, you want to have a second logical qubit and a third one, and so more. And the codes that we are implementing here have a property that we call transversality. A transversal code really means that the gate operation that you want to do, say, between one logical qubit and the next one, breaks down to making a gate operation in the same way, just between 2 adjacent qubits. That's what an implementer really wants, and this is why we looked into the color code. But that calls for, say, a square lattice, or say an ion array architecture. And we have worked on this for a long time. Unfortunately, it never worked out for some technical reasons, and for this reason, we just teamed up with the Infineon company for microfabrication. So the more recent chip, we reduced things not just to a lattice, but just to 2 parallel lines right here. And of course, it has now a proper multi-layer design, which allows us to do this. Just to make a long story short, we now can store, say, ions along these sides right here and bring them either together this way and brings them together this way. And in fact, we can rearrange the lattice, say, from a square lattice to a triangular lattice if we want that, and make them interact. These differences, the distances between these ions are still too big. And currently, we are still downsizing this together with Infineon to go to a lattice. such that eventually, and that is the vision that we have, we come down to a system which looks like that. Many ions, say for instance 10 by 10 or eventually 30 by 30, are hovering above a chip, and we apply address beams to the gate operations, to the entanglement, and have everything sitting here on such a surface. So with this, I'm here at the end of my talk, and just want to give you my dream and the vision. We want to have local logical qubits. It's just not 5, probably more like 10, including the ancillas and the flag qubit. But we want to protect each individual logical qubit by error correction, and we want to interconnect these groups of logical qubits by, say, dipole-dipole interaction, could be on a chip, or by even ion cavity interfaces, say, across an optical fiber. So these things would work out. Such that we come up with a conclusion and the future goals for this. We definitely need more qubits. So we want to go to 50 and 100, and then want to have this in parallel. This is a string of 59. We have up to 100 ions in the traps anytime. We need better fidelities. This is what we are working on every day, faster gate operations, faster detections. For this, we need technological advances, cryogenic traps, microstructured traps. We need to develop 2D trap arrays. You've seen the Infineon technology, onboard addressing, onboard electronics. This is on the way. The still open question is, how do we characterize larger systems? Because measuring entanglement in the system is important, and this is ongoing research. Implementation of quantum error correction is what I call, is really the holy grail of the entire system in order to keep the qubit alive for the computation. Once you have that, then the applications, like for instance, small scale quantum information processors for repeaters, or even more enhanced metrology, quantum metrology, more quantum simulations, even of 2-dimensional and 3-dimensional systems, and then full-blown quantum computation will be in sight. So this is, of course, what we have right now, and we try to expand on this. This, of course, is the doing over many years with very many people involved here. You see a large group, a number of people. This was at last year's group meeting. And of course, this would not be possible without the help of very many theorists that we have, among them predominantly, of course, my good friend Peter Zoller, with whom we have done much of this work, but many others as well. Here are the names, just in case you wanted to see the names. And here is where we are. This is where I'm sitting right now, right next to the airport. You heard the starting and landing aircraft right here. And this is where the quantum computer in Tirol sits. And right now we even have a new company, which is called Alpine Quantum Technologies. And the newer product that we have is that we have these two 19-inch tracks, which are not as tall as the one that I showed you. They're even more compactified, and they contain everything. You see, that's the inside. You see, that's the trap module. This is the laser module. The rest is electronics and control modules. And if you really want to know more about this, I would refer you to the CEO of the company, Thomas Mons. And this is a machine proudly made in Tirol by AQT. And here is my final slide. This is everything that's over from an ion trap. That's where the quantum CPU is residing. Thank you very much for your attention.
Can we take a few questions?
Sure.
So we have some questions online. Let us take those. Mrinal Giri, can you unmute and ask your question? Are you there? Go ahead.
Hello. Yeah, my first question is that how do they consider, basically you are saying that only nearest neighbor interaction hopping terms. How do you handle for to next nearest neighbor interaction term or nearest neighbor hopping in gate-based operation actually?
I have not understood the question. You're talking about the nearest neighbor interaction, or what is it you're talking about?
Hello.
Sorry, just acoustics. I couldn't understand you acoustically. Can you please repeat the question?
My question is that you consider when you gate-based operation, consider the nearest neighbor hopping term and nearest neighbor interaction terms in 1D array of qubit. Then how do you handle if we consider the next nearest neighbor interaction term or long range interaction term?
Yes. First of all, the connectivity in an ion trap, it can be all to all. So if you do computations on, say, with the modes of the motion that we have, then we have clearly all to all connectivity. We are not talking here about the quantum simulations where we just can adjust the JIJs. When we talk about real quantum computation, we have all to all connectivity. In fact, if you really want to exclude that, or if you want to have a different arrangement, then we use so-called hiding operations. That's what we use to reduce or to enhance the computational subspace. So, for example, if you don't want, say, the ion right next to you not to contribute or to be influenced by anything, you just hide it. Otherwise, it's in the same loop. It's contributing to the computation, and the good connectivity that we have really saves us quite a few quantum operations. Whereas, say, in a superconducting quantum computer, you have only nearest neighbor interactions, and you have many swap operations which we can forego. Does that answer your question, or is there anything else that I haven't understood?
I think that is right. Most probably, I don't know. And second question is that how do you in for trap, right? Then if you consider the more than one atoms at a you probe in quantum machines actually? How do you probe them if there is a two atoms reset at the same side or three atoms reset at the same sides?
I'm not sorry. Acoustically, you're very hard to understand. Can you just repeat your question really slowly?
I'll repeat. I think he's asking, how do you know whether there is one ion or two ion at a site? I think that's a very easy thing to do.
There's only one ion at the site because
you cannot have Coulomb repulsion. You cannot have.
Yes, there can't be two ions there. The ions are repelling each other.
Another question, Navneet, can you unmute and ask your question?
Yes. Hello, everybody. Hello, sir.
Go ahead.
Please go ahead.
Okay. Sir, I wanted to ask about. Oh, I'm so sorry. I'm so sorry. I wanted to ask about, like, we talked about the error. We need to control errors in our future vision. You talked about your future visions, and you said that we need to control errors in our system, right?
Yes.
So I wanted to know about, like, can you please explain a bit further more about this? Like, how can we do this, or how it is done? If it is done already, can we know about how it is done? And if it is not done yet, then how do we plan to do it?
Let me just try to explain this to you. This has been done, and to a certain extent, but it has not been done that we can break even, meaning that we can keep the qubit alive yet. That has not been reached. But let me just show you how this is achieved in quantum error correction. Suppose you have one qubit. The qubit, let me just go one step back right here. The qubit needs to be encoded. And let me just give you a simple example first. Suppose you have one qubit, which is a superposition of, say, 0 and 1. So you have alpha times 0 plus beta times 1. This is your qubit. In order to protect it or to correct, say, what kind of an error can happen? There's two kinds of error that happen in such a system, because there could be an error to alpha or beta. Or in other words, if you have a Bloch sphere and you have the error pointing, the arrow giving you the quantum information could point somewhere, the error could tilt. That would be a sigma x error, or the error could rotate. That would be a sigma c error. So we can describe every error in a qubit by sigma x or sigma c operations. Now, in order to know what happened, we need to create redundancy. For example, in classical error correction, in order to see whether an error has happened, you want to transmit, say, data from A to B. And then you have zeros and ones. Instead of transferring just 1 0 and 1 1, per bit, you are transferring 3 zeros and 3 ones. And then you take at the receiver station B, you just take, say, a majority decision. And if you have a packet which is 001, you know, okay, there must have been an error. This is definitely 0. But if you see a packet which is 110, then you conclude that must have been a 1, meaning that you can detect and thus correct only one error. This would be 3 qubits. It's 3 bits. For a qubit, since we have 2 errors, we need at least 5 qubits to do this. And this is why you saw the 5 balls right next to you on that plate. For more intricate codes that have, say, better features, you need a bit more redundancy. And this is done right here. So suppose you have now 7 of them. And these 7 qubits, they just store all the information in a topological way. Topological meaning in the following way: this is in the arrangement of the system. And this bookkeeping arrangement in the triangle shows you this triangle consists of 4 different plaquettes. So no matter what the ions right here are, we have a procedure with which we try to encode the information of a single qubit by entangling all of these 7 qubits. But then we can just check by going around 1, 2, 3, 4. This is 1 plaquette. Did an error occur or not? If there's no error, then measurements like, for instance, say the so-called stabilizer measurements, C1, C2, C3, C4, this is a measurement of sigma C, sigma C2, sigma C3, that would be the population. Here, if that is 1, then no error has appeared. But if there was somewhere a spin flip, then this would have shown up. This is measuring the phases. This, depending on how you do it, you have to make a spin flip first and then you measure. That's why this is called sigma X, whatever. So in other words, if you measure these stabilizers, then you know that within that plaquette a certain error has happened. You do the same for this error, if it's this plaquette, and for this plaquette, and then you come up with a table. That's why I said this is pretty complicated. Don't worry about this. This is bookkeeping, and the classical computer knows once you've made all these stabilizers, these measurements, then the computer knows precisely on which of the qubits an error has happened. And then you can undo it. And then this is what we call the logical qubit. This is how we do this. This has been done. All of these procedures have worked out. But now the question really is, how well can you do it? Because in principle, each of the operations could have another error too. So in fact, one would probably need another layer or 2. So some people think we need about 50 or even 100 qubits in order to safely store the quantum information. That depends on the quality of the fidelity of the gate operations. And for this, you can calculate from a threshold theorem what the threshold really is. And if you remember on one of the first slides I showed you, we are calculating a threshold for error correction in our system of, say, 10 to the minus 4 to 10 to the minus 5-ish. And that means once we get there with the fidelities of everything, including the measurements and the state preparation, on the fidelity of, say, 10 to the minus 4, then we are done. Then we can do error correction, which just keeps the system alive. So far, we have shown that all of these systems work, that all of these procedures work, and that we can just encode the system, we can decode the system, we can correct the errors, and we can go there. In a more recent paper, I didn't have the time to talk about this yet. This will come out in Nature in a few weeks from now. You will find that we have used 2 of these logical qubits where it even possible for us to correct the errors in a fault-tolerant fashion. And we were able to demonstrate that you can make a universal set between 2 logical gates. And this gives you better results than with fault-tolerant operation than without fault-tolerant operation. But we were not able to break this barrier, the threshold over all of these operations, to keep the system alive yet. So in answering your question, this is a crucial problem. This is what I call the holy grail in the system, in all of quantum information. We need to come up with sufficient fidelities and quality of the measurement to keep the system going long enough such that error correction really helps you. Once this is implemented, then you can do that. That's the idea. Does that answer your question?
Yes, sir. Thank you very much.
Thank you. That was great. Is there any question from the audience here? If not, we'll take, maybe can we take one last question?
Sir,
maybe?
I have a question.
You have? Okay,
Yes.
go ahead.
So my question is how we can define the totalization and what is the need of totalization?
Say again, how can we define what?
Totalization, because you show that there's some trotter time slices.
Oh, the trotterization.
Yes, sir. Yes, sir.
Yes, how we do this?
Yes, sir. What is the need of totalization and how we can define it?
What do you mean by defining it? It is defined simply as this the approximation of a Hamiltonian, of the dynamics of Hamiltonian. Let me just see where do I have where I have it. Just a second. Here we go. See, you write down your Hamiltonian first, and the Hamiltonian you write down in the individual parts. These individual parts, if they commute, then you're essentially done, because then you can just implement your unitary right away by raising this to an exponential. But if they don't commute, then you just break it into such parts that you can raise it to an exponential that gives you a unitary. And that unitary that you have here is just one unitary here. And then you have all of these individual steps, and then you can implement them. This is what's meant by trotterization. And this formula, that this unitary operation is approximating this dynamical behavior of the entire Hamiltonian, is a proven Trotter approximation, ProtoSuzuki approximation. So that is the procedure that you have to go through. And then, of course, the next step for us as implementers, as doing this on a quantum computer, is how do I translate this individual Hamiltonian to the unitary right here? And this, but this can be done with the toolbox operations. If you remember the toolbox operations that I've shown you before, the toolbox operations are just basic unitaries. And these basic unitaries are just replacing all of these entries right here. And then they just apply them to these Trotter steps. And then we do this just one by one, right after another. This is a sequence. It takes maybe a millisecond or 2 milliseconds. And then finally, you just get the result. I'm not sure, is that answering the question that you had?
Yes, sir. Yes, sir. Thank you.
Okay.
If there are no more questions, maybe we can thank. There's a question in the chat box. The last question. Can we take one more question, Professor Blatt?
Absolutely. Sure.
Yes. Ishitwa, can you unmute and ask your question?
Good afternoon, everyone.
Right.
Sir, in the first slide, you have mentioned about entanglement measurement, entanglement fidelity measurement using parity oscillation. So can you, sir, little elaborate on that point?
Yeah. Instead of in order to measure entanglement, you would usually have to make, say, a full-blown measurement of what this tomographic procedure. Tomography is inherently time-consuming and it's because it scales exponentially. So in other words, if you want to determine entanglement in a general fashion, there's hardly any other way to go than going to tomography, and that's very hard. But if you know you have a specific state, like a GHZ state, the GHZ state is the generalization. Let me just try to find it. A GHZ state is the generalization of a belt state. A belt state, that's the off-diagonal one. Let's just take the belt state where you have, say, GG plus EE. If you have GG plus EE right here, then of course you have, this is GG, that would be the element right here. That would be the diagonal here and the diagonal there. And the off-diagonal is just the corner and the other corner. So if you had that, for example, or even that one, so these are only 4 entries out of this which are of which are different from 0. The Greenberger-Horn-Zeilinger state is the same state as a belt state, just with more ions or more qubits. So for example, take 3 qubits, then you have the state GGG plus EEE. So 3 times in the ground state plus 3 times in the excited states. So that's this kind of a superposition that you have. Now, then the matrix would be, the corresponding density matrix would be that you get an entry on the first row, on the last row, and here on this corner and the other corner. So there's only 4 elements. And if you now make a measurement, which are just, say, asking for the populations right here, minus the off-diagonal elements right here, then you get the maximum contrast. That's what we call a parity signal. And that, if you know the state, like a GHZ state, for example, then you can measure this entanglement of specific states via parity oscillations in a much simpler way, because you know what the state is. And then that's the reason why using belt states or a GHZ state is the easy way to infer entanglement. On the other hand, when you have a very general state, which has, say, matrix elements all over, and you don't know what they are, there's just no way that you can just figure that out by parity calculations. So you would have to go through the procedure to measure all the off-diagonal elements by full tomography. We have done so once for a so-called W state many years ago with 8 ions. That took us a whole day to measure it, and took us 4 weeks to reconstruct the entire state on a classical computer. That can be done better these days. There are different procedures, but nevertheless, this is very time consuming, and this is still a matter of active research. How do we characterize entanglement in such a complicated system? If the system is easy, then parity oscillations are the way to do it. Otherwise, sorry, you have to go through hard procedures.
Yeah, understood. Thank you, Professor.
No more questions, right? Okay, so let's thank Professor Blatt once more. So thank you for a wonderful lecture.
Thank you very much, and I apologize again for having the time shifted. Thank you for your flexibility, and I wish you a very nice meeting, ongoing meeting. Take care. Hope to see you soon in person somewhere.
Sure, sure. We should certainly like to have you here in India sometime for a real physical meeting. That would be wonderful. Okay. Yes.
Very good. My best regards. Bye-bye.
Bye.
Thank you, sir.